in this section, we're going to be talking about combining functions. Now, there are two big ideas that we're going to have to talk about in this section right here. The first one is going to be the algebra of functions, which is very straightforward. In fact, you already know how to do this one, so I'm not going to really hammer down too many examples, but it's the second one here, and I'll do a bunch of these examples, which will be compositional functions. Okay, so without further ado, first we just have the algebra of functions. Like I said, very straightforward. You already know how to do a lot of this. It's just we need to define this so we can go into composition functions. So for two functions, sorry, I got a new computer here, and I'm learning how it writes and how hard I got to press on it and everything. So for two functions, we'll call them f of x and g of x with real number outputs. We define new functions as such. We can do f plus g. We could do f minus g. In other words, we can add the two functions. We can subtract the two functions. If we wanted to, we can multiply the two functions. And then you can also divide functions, provided that your second function, g of x, does not equal 0. I omitted the x, but technically, if I just put all this in parentheses like this and put a little x on the outside, then you have all the functions that you need. And this is nothing more than just the algebra of functions. So I'm going to do like I said, a simple example here. So here's our example. Find f plus g, f minus g, f times g, and f over g if f equals x minus 1 and g equals x squared minus 1. All right, so I'm just going to go right down a list. So f plus g. Now remember, always put parentheses first, then make your substitutions. So this will be x minus 1, and this will be x squared minus 1. Remember, this is f plus g. Now, group like terms if you can. X squared plus x minus 2. So there's going to be f plus g. Now we're going to do f minus g. So this will be, remember, parentheses first, then make your substitutions. So we're going to get negative x squared plus x, and then this is going to be negative 1 plus 1, which is 0, so we just get negative x squared plus x. For c, f times g, make your parentheses, then your substitutions. Looks like here we're going to have to distribute. So x times x to the second is x to the third. X times negative 1 is going to be minus x. Notice I left a little space there. Negative 1 times x squared is negative x squared. Negative 1 times negative 1 is positive 1. And I'm just going to come straight down. X to the third minus x squared minus x plus 1. So there's f times g. And then finally, the last one, and this is the only one where you need to be very specific, is f over g. So we have x minus 1 over x squared minus 1, provided that x does not equal plus or minus 1. Because remember, you got to state the domain. We're not allowed to have negative 1 or positive 1 in our denominator. Okay? So now I'm going to define the composition of functions. So what I'm going to do is pause the video, write out the definition, unpause it, and then you can pause the video, write it down, and then I'll read it, or we can read it together then. All right, so it's a whole page definition, but it's really important because we see these a lot in calculus and everywhere else. So when the output of one function is used as the input of another, we call this entire operation a composition of functions. For any input x in functions f of g, this action defines what we call a composite function denoted f composite g. That's how you read that. It's an open dot and it's read f composite g. So f composite g of x is equal to f of g of x. The domain of the composite function f composite g is all x such that x is in the domain of g and g of x is in the domain of f. Okay? So a couple of things here. First, when we look at the notation, what we do here is we evaluate the inside function first. Then we're going to evaluate the outside function. Now, earlier, last week, I said something along the lines of we can think of a function as like a calculator. Well, here is a situation where you actually have two calculators. And they're back to back. They're in a chain. The first calculator will be g of x. Then the second calculator will be f of x. All right? So what's going to happen here is this. Let's say you put x on this conveyor belt. You have no idea what x is, but what you do know is when you turn it on, the calculator is going to calculate its numbers, and it's going to output g of x. Then g of x goes into this calculator here. It's going to calculate, and then this output will be f of g of x. And that's what we mean by a composite function. You evaluate the inside function first, and then you evaluate the outside function. Now, this idea of domain, here's the thing. You got to make sure that whatever x value you use for g of x, you don't break the first calculator, which means if you have a restricted domain for g of x, this restriction will carry all the way through this composite function or this calculator machine, okay? Otherwise, sometimes you may have a restriction in f of x. And if you got a restriction in f of x, then you need to be really careful about what g of x outputs, because you want to make sure it doesn't output something that is going to break the second machine. So it's always good, whenever you're doing these, to check the domain. Now, initially, we're going to do some easy ones where the domain will be all real numbers, that we won't have to worry about domain. What we want to get used to first is just, number one, identifying the composite functions. Number two, evaluating them, okay? So first thing I want to do is let's go ahead and let's look at this question right here. And this is a very, very special question, and you're going to see this no matter what class you go into. Let's determine whether f of x equals 2x plus 1 and g of x equals 3 minus x. So determine whether these two functions and their composition is commutative. All right. Now this commutative property, this is one of those properties that, we learned a long time ago and we never ever think about it again, but it's pretty self-evident. So if you forget what the commutative property is, commutative property just states 2 plus 3 equals the same thing as 3 plus 2. In other words, order doesn't matter. So what I'm asking in this question, does f composite g of x equal g composite f of x? In other words, can I just switch the way these functions look and still get the same exact output? Well, let's find out. So I'm going to do this using that calculator setup again because I think visually it really makes a lot of sense. So here's part 1. We're going to do f of g of x first. Now, remember earlier I said you're going to do the inside function first. So first thing we're going to do is evaluate g of x. Now, g of x is just very special. It's 3 minus, and then remember, put a parenthesis. And then the second machine is going to be f of x, or the second calculator. And that's going to be 2x plus 1. Now, what I'm going to do is put the letter x in the calculator. And I'm going to hit the enter button. X falls down into here. G of x will spit out 3 minus x. Now, this will fall down into the parenthesis there. And what you get out is going to be 2 times a quantity, 3 minus x plus 1. And if you wanted to, you can simplify this into 6 minus 2x plus 1, or just simply negative 2x plus 7. So this is f of g of x, okay? Now, in order to demonstrate if this is commutative or not, commutativity is what the fancy math people say, we're going to switch the order in which we evaluate, okay? So here, the first thing we're going to do is we're going to do f of x first. And then we're going to do g of x second. So remember, f of x is going to be 2 parenthesis plus 1. G of x is going to be 3 minus parenthesis. And we're going to make the same substitution that we did previously. So we got an x. We turn on the calculator. And we get 2x plus 1 as an output. That output is going to go directly into the input for g of x. And then if I simplify this, notice we get 3 minus 2x minus 1, which is going to be negative 2x plus 2. This is g of f of x. And notice these two are not equal. So compositional functions. Thus, the composite of functions is not commutative. In other words, you cannot just switch them and think you're going to get the same exact thing. You're going to get 2 completely different answers. Okay? So the next example here, let's go ahead and evaluate. So given f of t equals t to the second minus t, and h of x equals 3x plus 2, we're going to evaluate h of f of 2, and then we're going to do h of f of negative 2. Okay? And yes, these are written correctly. F of t is correct and h of x is correct. So let's go ahead and let's do the first part. So remember, and I'm going to do this 2 ways. I'll do it using the calculator thing, and then I'm going to do it just using algebra. All right, so here we go. So we're going to draw the picture first. Make sure we give ourselves enough space for stuff. All right. So remember, we evaluate the inside function first. So this is going to be f of t. So let's go ahead, let's label it. Second will be h of x, and let's go ahead, let's label this. Now, according to the input is going to be 2. So I just put it in the calculator and go ahead and hit enter. 2 falls down into those spots respectively. You get 2 to the second, which is 4, and 4 minus 2 is 2. So 2 comes out. It's going to fall down into here. 3 times 2 is 6, and 6 plus 2 is 8. So h of f of 2 equals 8. I think very straightforward. Now, you don't have to draw this machine stuff if you don't want to. It's entirely up to you. But if you didn't want to, what you could do here is just say, well, this is going to be h of 2 to the second minus 2. Like you can go directly into this if you can see it that quickly. Some of us can't, and that's okay. So this is nothing more than just h of 2, which is going to be 8. All right? So if you can see it, good. If not, it takes you an extra 30 seconds to draw it out, and it's really, really easy. So we had one more to do. And that's going to be h of f of negative 2. All right, so once again, I'm going to just draw my boxes here. I highly recommend the box idea. It's super easy. And then once you get really good at this, like I said, you'll be able to see things. So I'm just going to go ahead and just label everything. There we go. And we put negative 2 on a conveyor belt. So when we turned it on, when I was taught, these were function machines. But now, and I'm kind of dating myself, everybody has calculators. So I thought to myself, why am I going to call it a machine? I'll just call it a calculator. But I always refer back to the machine, and it's my fault. But anyways, we can get through this. So I turn on the calculator, hit enter, and negative 2. So this is going to be, what's this? Positive 4 plus 2. So it outputs a 6. That output is the input for h of x. 3 times 6 is 18. 18 plus 2 is 20. So h of f of negative 2 equals 20. Okay? All right. Now, here comes the domain part. And like I said, this part is the part that always gives, it'll give us some trouble. All right? So the first thing I want to do is I want to give us steps. So steps to find domain of composite functions. This is really, really, really important. Because like I said, you don't want to put something in the calculator and then the calculator breaks, and then you can't even evaluate the second function. So, we're going to assume that we have f composite g of x, which we know is f of g of x. Okay? So step 1, we're going to find a domain of g. Okay? Step 2, find the domain of f. Pretty straightforward so far. I know you're expecting this like real big crazy thing, but no, that's the first 2 steps. Find a domain of g, find a domain of f. Now, step 3, find those inputs x in the domain of g for which g of x is in the domain of f. That is exclude those inputs from the domain. Sorry, this is a big definition, but we'll get there. Domain of g for which g of x is not in the domain of f. Okay? So go ahead, write that down. Pause the video if you must. But I'm going to just go right into an example. And you're going to see this isn't as hard as what it sounds like, but we do need to be careful. So here's our example here. So we want to find the domain of f composite g of x, where f of x equals 5 over x minus 1, and g of x equals 4 over 3x squared minus 2. Okay? Now, already on the surface, remember, we are evaluating f composite g of x, which means we know, according to the way that we set this up, g of x comes first, f of x comes second, which means we need to make sure that whatever numbers we put here, all right, will work for g of x. Also, the outputs also have to work for f of x. So, step 1, let's find the domain for g of x. For g of x, the domain will be 3x minus 2 equals 0. Technically, what I like to do is I will put not equal to 0, and I just solve. X cannot equal 2 over 3. Okay? So here's the first thing. All right? We know, no matter what, if we use 2 over 3, the very first g of x, and I'm going to color it in red, it'll break if x equals 2 over 3. Now, second, we know that f of x's domain, all right, would be x minus 1 cannot equal 0, so x cannot equal 1. So not only can we not have x equals negative 2 over 3, we cannot have, now listen, don't jump to any conclusions. We can't have, I'm going to write it down, we cannot have positive 1 as an output of g of x. All right? So I need you to think about this, because I know a lot of us may be saying, going, oh, well, domain of f, you can't have 1. All right? But you got to understand, this is a composite function, which means the thing that, and I'm going to zoom in. So make sure you're watching the screen, upper right-hand corner. I'm going to zoom in here. So here is what I'm talking about. This output right here in the middle, we cannot have x equal 1 there. Like, we can't have that, because then this will no longer work. This will definitely break. All right, so the output of g of x cannot equal negative 1. So how do we find that? What we say is g of x cannot equal 1. All right? So what we're going to do is we're going to find when will g of x equal 1. In other words, 4 over 3x minus 2 equals 1. And let's go ahead and solve for x here. So just multiply both sides by 3x minus 2. So I'll just show that right here. That's going to give me 4 equals 3x minus 2. Add 2 to both sides. 4 plus 2 is 6. This is going to be 3x. Divide both sides by 3. X equals 2. Okay? So, what output will make f of x have a 1 in the denominator? X equals 2. So this is the number we also need to exclude from our domain. All right? So therefore, the domain for f composite g of x is, we write all real numbers comma, but x cannot equal 2 over 3 and, or we'll say or, positive 2. This is our domain right here. All right. Now, the 2 over 3, very self-explanatory. Let me write down the functions again. G of x equals 4 over 3x squared. F of x equaled 5 over x minus 1. Now, remember, you evaluate g of x first, then you evaluate f of x second, okay? We already know 2/3 will break this. All right, it's broken. Game over. However, if you put 2 on this conveyor belt, look what happens. We know we evaluate g of x first. So it's going to be this. Now, if I let the 2 fall down into here, I'm going to get 4 over 3 times 2 minus 2, which is 4 over 3 times 2 is 6, and 6 minus 2 is 4. And notice you get 4 over 4, which equals 1, which means the output here would be 1. But we know, since this is f of x, that will completely break this second machine. All right? So we can use any number we want. We can use all real numbers except 2/3 or 2. Can't use those because we break either machine, okay? Like I said, compositional functions and their domains are a little bit different from just domain in general, okay? So let me show you another one here, okay? So we're going to find a domain. Of f composite g of x, where f of x equals the square root of x plus 2, and g of x equals the square root of 3 minus x. Okay? Now, once again, it really helps if you take the time and you just draw these. We know g of x is first. Okay? We know f of x will be second. So, right now, right now, I know I'm looking at, number 1, 3 minus x has to be greater than or equal to 0, which means if I solve it for x, this is what I get. However, I hate the way that looks. I always like to draw the variable first, coefficient, or the constant second. So no, I know I'm allowed to use numbers of x that are less than or equal to 3. Okay? Now, we need to be careful about this. Okay? Because we also know for our second machine, x plus 2 greater than or equal to 0. Notice, negative 2, there we go. So notice here, I can only use values of x that are greater than or equal to negative 2. So there are a couple ways to think about this. The first way is a simple number line. All right? So on a number line, you have 0 right down the middle, and what I'm going to do is I'm going to graph both of these. Notice the first one says x has to be less than or equal to 3. So for me, that'll be a bracket facing the left, and I would shade everything to the left. Now in blue, this is going to be x is greater than or equal to negative 2. So this will be shaded this way, okay? Now, here we can see that we have the red shading and then the blue shading, okay? But remember, I said this a long time ago. Well, I said it earlier, not a long time ago, a couple minutes ago, which is this. If there's a restriction on the very first function that you evaluate, that is going to carry itself through the entire composition. Now, if we look here, and I'm just going to go ahead and just substitute in some numbers, and we should be able to do this, relatively quickly in our head. So if I put a 3 here, I get 0. That's okay, because the output of 0 comes here, goes in there. Still got a positive number underneath f of x, which is good. Okay? Now, if I put a 2, 3 minus 2 is 1. That's still fine. If I put 0, we get 3 minus 0, which is 3. If I put negative 1, well, we have a negative and a negative. It makes it positive. So this is going to be 3 plus 1, which is 4. Square root of 4 is 2. So notice that as long as we have this situation right here, x is less than or equal to 3, our outputs will always be, so I'm going to write it like this, our outputs will be greater than or equal to 0. In other words, it's going to be the smallest it gets is 0, and then it just stays positive, and it keeps getting larger and larger and larger. So even though we know that we cannot, that for the domain for f of x is greater than or equal to negative 2, we never even have to worry about this, because no matter what, we will always get this positive output, which is exactly what we need. So our domain for this problem right here is strictly negative infinity all the way up to and including 3. Okay? So that's one easy way to look at this. The other way to kind of look at this, all right, is to do it algebraically. So for f composite g of x, this is going to equal the square root of the square root of 3 minus x plus 2, which simplifies down into square root of 3x, or 3 minus x plus 2 is greater than or equal to 0. In other words, let me show you where I got this from. Here is my radicand of the major square roots. So what I'm really concerned with here is as long as this is greater than or equal to 0, then I can always evaluate. Okay? So what we have here is this. The square root of 3 minus x plus 2 is greater than or equal to 0, since the radicand of a square root must be positive. In other words, since this thing right here, let me be more specific here. Let me zoom in. We know this has to be x is greater than, or I'm sorry, other way around. X is less than or equal to 3. We know this is always going to be positive. It's always positive underneath this radical symbol. So because this is always positive, and you're adding a positive, it's always going to be greater than or equal to 0. Even if x equals 3, if x equals 3 here, you're going to get, and I'm just going to erase, you're going to get 3 minus 3, which is 0, and 0 plus 2 obviously is greater than 0. So that's what we mean by that. Okay? So let me write it out one more time. There we go. So since this is always positive and you're adding a positive, the radicand of a square root must be positive as well. Okay? Therefore, this is going to be positive, or 3 minus x is greater than or equal to 0, and we just went ahead and solved this. We said 3 is going to be greater than or equal to x, which I hate the way that looks. I like to write the variable first and the number second. So as long as x is less than or equal to 3, you'll always have positive numbers, which means it'll be completely defined as long as x equals or I'm sorry, as long as x is less than or equal to 3. So once again, your domain is negative infinity all the way up to positive 3, including 3. So here are two examples. Here are two examples where this example right here, the one we just did, we had a restriction on the very first, and that basically carried its way through. Okay? Now, in the previous example, we also had another restriction. All right, we had, let me do this. There we go. We also had another restriction. It's right here. Okay? And that not only carried itself through, but it also influenced the domain for the next function. So all I got to say is this. Follow your steps. Please be careful. And you need to think about what's happening. Okay? When all else fails, graph it. See what it looks like. Okay? So maybe I'll put that in like step number 4. Put it in red so we know it's like very last ditch effort. When in doubt, graph. Okay? All right, so real quick with that very last one, because I know that one's going to give us a lot of trouble. When in doubt, just graph it. So we got 2 square roots, 3 minus x, plus 2. And notice, in green, and I'll zoom in for us. Oh, that's way too much. Notice it starts at 3 right here, and it stays negative. So 3 to negative infinity. Okay? So when in doubt, just graph it. See what happens. If you have any questions, just let me know. I'll be around. Talk to you soon. Bye.